last topic, the transformations of graphs by changing of variables. That's what happens. Is ultimately it is the change of variables. And every function has two variables: input, output, independent, dependent variable. They play different roles. And that is why when you change one or the other, the effect is different. So and even geometric, as you can see, the end result is different. And before we proceed to dealing with those problems as we started last time, let me give you a summary. And I'd like to try to put it in a table. So if we have horizontal and vertical transformations, the table is not really that big. So the vertical is the simpler one. It is the one that is about y, and horizontally about x. Okay, so we have shift by k or by s, flip, and stretch by k. Okay, so the vertical is very straightforward. You do what you see, you do it to y. Okay, so then if you start with y equal f of x, what has become of it is y is equal to f of x plus s. So you can almost see how y was something and then we added s to it. Similarly, y is equal to negative f of x. There's the flip, multiplication by the negative sign, and stretch is you multiply by k. Okay, everything changes. Well, let me maybe rearrange the terms here and put the function followed by the operation. So I multiply by -1, I multiply by k here. Okay, so this is how the transformation that does something to y, to the y-axis. What does it do to the function algebraically? And that's what it is. Add s, multiply by -1, multiply by k. K being a positive number. Okay. Now the horizontal, everything is the opposite. So y is equal to, you can see how the formula is different. X minus s. So first of all, everything is inside the parentheses. So that because x is the independent variable. So that's where it is located, sort of. When you do substitution, it's inside of f. It's what comes before f, like this. So f, and then you have x, and you have y, and then you can do the transformation. You either put transformation here, or you put transformation there, and these are two different ones. So this is the vertical one that comes after, or the horizontal one that comes before. The effect, as you can see, is very different. So this one is also different, but it doesn't matter because it is the same pretty much. So you multiply x by -1. You see the difference, right? So the multiplication by -1 is inside the parentheses. X is multiplied by -1. So every time the change is vertical, it's about y. The change horizontal is about x. Okay, so here and here, that's once again the opposite. Well, by the way, in the second row, multiplication by -1, why do I do exactly the same? Well, because multiplying by -1 is the same as dividing by -1. So that's why it doesn't matter, and it looks very similar. The second row is not as different as the other two. And here I do, instead of multiplying by k, I divide. So that's the table that contains everything that we have been talking about in a most compact form. Now, but what comes next is the really interesting application. It is we will try to take care of all quadratic polynomials at once with the help of this idea. So we already started on that. So and the idea is that the graph of every parabola of every quadratic polynomial is a parabola in the sense that If we have two different ones, we can transform one into the other by means of those 6 operations. In fact, fewer than 6. Why fewer? Because, first of all, we only need 4. Because we do not need a horizontal flip. If I flip horizontally my parabola over there, I will get the same parabola. So it's no use for us. And secondly, stretching vertically or shrinking horizontally is the same thing for these functions. And once again, we pick one of the two. And that's how we end up with only 4 operations. Okay, so that's what you see here. So the two functions we are facing. One, the original parabola of y equal x squared, and then some weird hanging down parabola on the right. Okay, the bottom. Okay, so how to transform one to the other? We just compare them, and since I don't have any markings or grid, so I just from the top of my head roughly estimate what has happened to the shape and the location. And that's what we have discovered. These are 3 steps over there. We compare shapes first, and it appears to be thinner or slimmer, which means that we either shrink horizontally or stretch vertically. We choose to stretch vertically because it is simpler. If you look at it, stretch vertically is you multiply by k on the outside rather than anything on the inside, which is just more complicated. Not significantly, but you just pick one of the two, and that makes your life easier. The second one, we choose orientation of the curve, and it is a parabola. The original one points up, opens up, and this one opens down, which means that at some point it will have to be flipped, and we did. And so we just write it down for now. Flip vertically, okay, and then finally location of the vertex, that I marked with red. Is elsewhere away from the origin, and that will be a shift, which is not simultaneously, but both vertical and horizontal. Okay, so we written it down, and then just one by one we carried it out in the order of orientation, stretch, and then location. Okay, so this is the table, or rather the sequence of events that you can see on the right. The original parabola, so it's kind of a medium built, and with a vertex at the origin. Then we flipped it, second stage, so original, flipped it upside down, so that way it already looks a bit more like the orange one we're looking for. Then we stretched it by multiplying it by 5. It appears to be so much slimmer that we multiplied by 5. Okay, so this is the next step. Vertical stretch by 5, so you multiply by 5 on the outside, keep x, we'll get to x at the last moment. And then once again, horizontal, it's a third horizontal operation. It is a shift, horizontal shift. No, actually it's vertical, or 3 vertical ones. Vertical. We shifted 3 units up. You see that one, okay. Vertical shift, and finally we have to execute the horizontal shift. And as you can see, it is 30 inches to the right, which means we subtract 3 from x. The last step. And the last one is the formula, right? So that will be the answer. You can certainly simplify it. So g of x is equal to -5 x minus 3 squared plus 3. Okay, so that works out. It is the worst case scenario, pretty much. So it will work out every time you can think of. So in order to make that clear, put it on record, there is a theorem. So every quadratic polynomial can be put in this form. Well, this is still to be demonstrated, but why the claim that I made that we can always do this has to be taken care of. So g of x is equal to let's say to a x minus h squared plus k. Okay, so I can point out the shift. The only one that concerns x is h. So this is the shift. So that's not part of the statement, but the vertex is at point hk. So that's the shift that we the very last two operations that we have executed was the vertical and horizontal shift, and that's what happens to the vertex of the parabola. The previous operations keep the vertex at the origin, as you can see, and but then the last two we still have to shift it, and that's what it's right there. Okay, so as you can see, what's left, the only parameter that is left is a. Okay, and a is the or rather say the absolute value of a is the ratio of the stretch or shrink, and the sign of a is the flip, if any. So meaning that if a is positive, there is no flip. If it's negative, there is a flip, vertical. So that's all there is. You can always execute it if you encounter anything elsewhere. It probably will be simpler than that as far as geometry is concerned. So you literally examine the graph of the other function and determine what is. Sometimes it can be done exactly. What parameters have to come into play. We were able to actually do it exactly over here. That appeared to be this is 3 and this is 3, and that is indeed the shift of the vertex of the parabola. So compare to the standard form of a quadratic polynomials, ax squared plus bx plus c. As you can see, the key thing to remember that a is the same. That doesn't change. So that coefficient that you see in front of x squared when you have a quadratic polynomial, that is the stretch factor. Stretch factor with possible flip. So if, for example, it starts with negative 3x squared, you know that no matter what follows, it is upside down and kind of slim. Okay. So then what remains is to demonstrate that this is indeed the case. We're not going to prove it. Let's have an example. And the operation that you may have heard of, we're completing a square. As you can see, it is a square. Compare the original one to the new one. There is that square over there. So that's what makes it possible. The whole thing possible is certain algebraic manipulation that turn the last one into the previous one, and that's called completing a square. I'll have just one or two examples of this to get started. But first of all, what is a complete square? It is two terms, let's say u plus v squared. This is the formula that you need to remember anyway. A complete square, also known as the binomial, also known as, I'm not sure what else, but it is in every book pretty much at the top of the list of formulas that you need to know. So it's not like trigonometric formulas. It's way more basic, and it's basic in the most literal sense, because if you go backwards, it's really no. If you can just expand, there is no trick behind it. It is you just expand in order to discover this formula. So you multiply u plus v by itself, and you end up with this. Well, if you don't believe me, u plus v times u plus v is equal to what? Is equal to u times u plus v times u plus u times v plus v times v. Okay, and then each on the left multiplied by either one on the left multiplied by either one on the right, you end up with 4 terms, and 2 of them are the same, and that's how you end up with u squared plus 2uv plus v squared. Okay, so there's nothing mysterious about it. The mysterious or important part about it is when you go this way. Okay, so you look at that expression on the right, and you're supposed to discover or realize or recognize that it is a complete square. So that's the challenge frequently. Recognize u squared plus 2uv plus v squared as u plus v squared, a complete square. Okay, so as an example, let's say x squared plus 2x plus 1. Is a complete square. What is it? You don't see it right away, match it up.
X plus 1 squared.
X plus 1 squared, right. Okay, so you, as soon as you matched up the terms appropriately, you will discover what that missing term is, and you'll have your answer. So how about 4x squared minus 4x plus 1? The first term, once again, I put them in the right order so that that's not the challenge. As you can see, it is in the standard form for quadratic polynomials. X's go down in powers from 2 to 1 to none. Okay, so once again, I match it up with u squared. So the first term is, in fact, if u squared, which means that what is u? 2x, right. And the last term is the last term is v squared. So what does, which means that what? Well, v is minus 1. Not 1, but minus 1. Why? Because that extra term, that extra sign over here, tells you so. If you're not sure, once again, come up with a conjecture, and then you just multiply out, and you will see whether you're right or not. So you always can the backwards direction is hard. The direct direction is okay. So you just multiply out. Okay, and so on and so on. That these are once again complete squares. You can recognize them. You can match them up. You can recognize them quickly if you already done it before. You can match them up the way we just did. You could also do some algebra in order to do pretty much the same. One way or another, you just or trial and error, all fine. But these are complete squares, and then what we're after, as you can see in the where we were over here, that extra term k over there, which means it's not a complete square. It is an incomplete square. How incomplete? That extra term, the vertical shift, is what makes it not a complete square. A complete square would be a quadratic polynomial that is also a complete square would be like ax minus k squared, and its graph is it might be stretched or even upside down, but it's definitely still passing through the origin. Okay, so that's what extra term is, and that requires extra algebra to worry about, unfortunately. So let me just do one example. Well, suppose complete a square. F of x is equal to negative 2x squared minus 4x plus 7. Okay, so one way is just to isolate x. In contrast to the last example, when we just looked at 4x squared and realized it's 2x squared. Okay, this one, 2x squared. And 1 is negative 1 squared. So that was the idea of how it worked out. Alternatively, you can factor stuff out so that you isolate x squared, rather, like this. So negative 2x squared plus 2x, right, plus 7, like this. Okay, so that way your complete square will always start with x plus something or x minus something. Yeah. Smart, you just look for smart parabola. Smart parabola, I don't do it. They may have, if you want to do it. Yes, one is. Is that what? Subscribing or the last working somewhere else. Yeah, you just the correct calculator. Or can now have that I don't know what calculator is. The pen is not working somewhere else. Okay, so as I was saying, the isolate x squared. Isolate x squared, so then you know how how your complete square will what it's going to look like in the beginning. It will have x plus or minus something. Okay, so that's an advantage, and the rest will just taken outside. There is a coefficient in front of it anyway, right? So some kind of a. And then so we isolate that out. We isolate that out too, so we don't have to worry about it. We end up with two terms instead of three. That's the problem, but really not a big one, because all you have to do is just to identify what they are. So x squared plus 2x. Let me just put this aside. What is the missing term? That's the question. Over here, I have to add a missing term. A missing term of this triplet. So it has got to be a square of what's left. So what is it? Look at the middle term. This is 2uv. This is u squared. Then I'm pointing out at this. Okay. So the first term is u squared. The second one is 2uv. You know what u is. U is x. U is x. U is x. And now you just determine what v is. What is v? 1. Okay, so once you know that, you know what the missing term is. The third one, v squared, and it is 1. Okay, so the missing term is 1, and that was the crucial step. So then this is a complete square, and you actually can finish the job if you like. It will be x plus 1 squared. Okay, so that will be the part of the answer. We just have to do a little bit more work to complete it, but that's not any trouble, because I need that missing term 1 over here, right? I need it, but I don't have it, so what I do is I add and subtract like this. Okay? That missing term, plus 1, I add and subtract. So that way I do have a complete square lined up. Okay, and then the job is almost done, because I already know what it is. It's x plus 1 squared, and then the rest will be just a little bit of simplification. So it will be negative 2 x plus 1 squared. And then what's left, this plus 7 still here. What's left is plus 2. Yes, plus 2. I guess I had a little typo there. No, that's not a typo. I guess I have a typo here. No. Yeah, I have a typo there. Okay, so this is okay. Okay, so then the answer is negative 2x plus 1 squared plus 9. Okay, let's make sure that this is correct. So like I said, it's an algebraic manipulation, so you have to be careful. But just keep in mind that this is where the key is. They are all equal to each other. That by the way is for, I never had the opportunity to tell you that the importance of those symbols. So and that when the time for the test comes, make sure that you have them all over. Equal, 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 equal. So if you're saying they're equal, you better write that they're equal. So that habit that frequently one might see, skipping equal signs is not acceptable. So it is this a missing verb in a sentence. So two things. 1 plus 1. This is not a sentence. Okay. 1 plus 1, 2. There is no verb. This is the verb. So equals or is equal to. That's, by the way, where, if I'm not mistaken, I think that's where the equal sign comes from. Those two L's, at some point, somebody turned it and made it equal from like 300 years ago or so. So I believe it was the very last step in the making algebra as we know it. So it took them a few hundred years to come up with, first of all, Arabic numerals, and then add, subtract, divide, multiply these symbols, and the equal actually was the very last one. And so it actually comes from English. So I guess they had been using just the word is as a substitute. You can take all the algebra and replace everything with those symbols. You can replace them with words, and then that should work out just fine. You will end up with sentences. Those sentences might be incorrect. It happens, but at least they are grammatically recognizable, meaningful sentences. So that's what you should try to have. Okay, so once again, why is it good? Then you can retrace the steps and verify whether or not what you have makes sense, or correct rather. The original function is here, and the last one is here. Is it the same thing? Well, you're saying that they are, so you can just verify that they are. So you verify, and you're working backwards, which is much easier because you just expand. So negative 2x plus 1 squared plus 9 is equal to negative 2. I expand the square, x squared plus 2x plus 1, simply through multiplication, and I have negative 2x squared minus 4x minus 2 plus 9, negative 2x squared minus 4x plus 7. Okay, so checks out. Okay, so then you know what you're saying. And if it doesn't match, if you have time on the test and you need to verify it, then you definitely should do it. So any questions about this? So it is certainly a certain challenge, primarily because it's so different from everything that we have been doing. Because purely algebraic manipulation of symbols, and it has to be done carefully. And the fact that things have to be equal to each other is just necessary but not sufficient to get there. So you have to steer yourself and transform a function into that formula into a form that provides you with that extra information. And as you can see now, it is a discovery that we have made through this algebra. Without plotting, we know what that graph is. How do you, looking at the graph, how do we plot it? That might be the second part of the problem. So once you found, you did the completing square, task. Step number 1. Step number 2 might be plotted. So without actually plotting it, you can just describe it by looking at these 3 or 4 numbers and tell what has happened. So f of x, it's the same function, so I'm using the same notation, negative. How about I put -1 here? Well, let me rearrange the terms so that they would kind of go in the chronological order. X plus 1, okay, squared. Okay, then what I do to it, I multiply it by 2, multiplied by 2, and then I multiply by -1. And finally, I add 9. Okay, so I try to separate different things from each other. Well, in fact, this one probably also calls for separate color plus 1. Okay. So as many different colors I've got, this is how many operations I have. I have four operations. I put them in chronological order, so in the way we're going to explain them. 1, 2, 3, and 4. So what are they? Number 1, what happens to the geometry, or what happens to the function, to the original parabola? Yeah. Yeah, left 1 unit, right. Okay, then number 2, stretch up, so vertically by 2, by a factor of 2. Number 3, yes, vertically. And finally, no, not horizontal, it's vertical. It's happening to y now, so it's up by 9. Okay? So, I mean, then once it's all listed, then it shouldn't be a big challenge to carry it out. So that's my regular parabola. And then the green one, I shifted 1 unit right. Okay, then I stretch it. Make it so same vertex. So it's still on the x-axis. So the stretch will make it will not make it move away from the x-axis. So that will remain the same because it's stretched away from the x-axis, up and down. So if it below goes down, if it above goes up. Okay, well, I don't like it. It still has, and it should not, I created by accident, I created a corner there, and there should be no corners here. It still has the smoothness.
Because of it being x plus 1 in the first step, should it be left?
I moved it, sorry about that, left 1, yeah, starting over. Okay, so let me put that point where it belongs. So this is my new vertex at -1. Okay, otherwise the shape does not change. So try to reproduce that as careful as you can. Same shape. Okay. Then the stretch, as I pointed out, it's stretching is slightly trickier because it gets closer. It is non-uniform in the sense the shape changes non-uniformly, but I try to. Okay, and then the third one is a flip. So I take the purple one and flip it upside down. The slimmer one, and finally I move it 9 units up. Well, okay. 9 units in the vertical direction. Okay. So it's the main thing about it is certainly just to remember that there is basically only one parabola, and the rest of the parabolas, all the quadratic polynomials, are really made from it. And you can see it algebraically, you can see it graphically, how they actually transform into each other. Okay, so and then it takes a certain skill to algebraic skill to transform a function into the next. But once you do, this is at the bottom is pretty much what your right away you have a sequence of instructions of what to do to the xy plane. So take the xy plane, shift it left one, then stretch vertically, then flip, and then lift it up by 9. So it's like another function, but this time a function that is not with numbers but with the plane. Okay, so transforming a plane, what we talked about previously, and that's what we're facing here. Okay, so we'll probably have to come back to completing a square more than once. But for the time being, we'll move on to the next topic. And it actually grows out of this topic. Are there any questions about this? So if we take another look at this table over here, and the difference between the vertical and horizontal behavior, rather y changing x affects the geometry in such a different way, and vice versa. And let me just remind you of where this one comes from, where the formula comes from. It's very simple. So if we're doing a horizontal shift by s, okay, so a shift horizontal by s means that xy goes to a point which is x plus sy, plus s as you think. Okay, so where does the minus come from? It's when the function comes into play. So if this one lies on y equal f of x, and this one lies on y equal g of x, the new one. So this is the old one, and this is the new one. Okay, so then if x plus sy lies on the graphical function y equal f of x, it means that y is equal to g of x plus s. Which is also equal to f of x. So then it seems that we have found g of x plus s is equal to f of s. But that's not good because the formula is just so awkward. It has the independent variable is some kind of expression there. I want to have there an actual variable. Okay, so that's why I need to do some algebra. So it's f of x over here. Okay, so how do I do it? So what's its formula? And the answer is here. I pick say choose u. And another name for the new function. We have created a new variable x plus s from the old variable x, and with respect to that variable, f is a function. Okay, so then so if u is the variable of my function, then I need to express x in terms of s. I'm sorry, x in terms of u, and x is equal to u minus s. We're solving this equation for x, and that's where the minus comes from. So u is equal to x plus s, which means that x is equal to u minus s, which means that f of we end up here with u minus s. Okay? That's where minus comes from. It comes from solving an equation. So the original relation between the two variables is very clear. It's right here, x and x plus s. Okay, so it is addition, as originally we talked about transformation of the plane. So if we shift to the right, we add s. Okay, but when we are trying to find the equation of our new function, we have to solve a certain equation, and we end up with subtracting. Okay, so and then look, go down to the second line. To the second line, we are in the same situation. We're solving an equation, which would be what? U is equal to x times -1. Solve, and x is equal to u times -1, or u divided by -1, the same thing. And that is why we have the formula in the second column, second row. Okay, the last column, second row, we'll multiply by -1. Okay, so that's the second one. This was the first one. The third one is also similarly u is equal to x times k. Solve, and we have x is equal to u divided by k. Okay, so that's where the very simple reason why we end up with these seemingly weird operations, because at some stage we have to solve an equation, and then you can see what has happened. Addition had turned into subtraction, and multiplication had turned into division. As it always when you solve equations, that's what happens. So it is, in other words, we work in reverse. We are trying to solve an equation. We're trying to undo the effect of an algebraic operation. Addition. How do we undo addition? We subtract. How do we undo multiplication? We divide. Okay? So that's one way to look at it. Another way is just to think about transformations. You stretched. How do you undo the stretch? You shrink. If you shift it left, well, how do you undo it? You shift right, and vice versa. So that topic is called inverse functions. Functions that undo the effect of each other. So algebraically, these are primary. Okay, here it is. The primary concern is algebraic operations, and that's where algebraic operations come from. Where did subtraction appear? You had an addition, and then you had to solve an equation, and then you ended up subtracting. You had multiplication. You didn't know anything about division, but then at some point you need to solve an equation, and you come up with an idea of maybe I start dividing things. So that's roughly how it works. Okay, so I'll just resume next time, I guess.